Okay, everybody, prepare for the wizard demo. This is one of my favorite demos, especially to do for like middle schools and little kids and stuff like that. This is actually the first time I'm ever doing it for my own kids. Hey man, coronavirus has its advantages, I guess. Okay, so
introduce us.
That is Audrey Breslin, and that is Conrad Breslin, right there.
Show us.
No.
Yeah, not on YouTube, bud. No. Okay. So, this is methanol. We've actually seen this before. We saw it in our whoosh bottle demo. The thing is that I added something special to make it a green flame. So one of the first things that you need for this demo to be kind of more spectacular, the reason that we use methanol is that it burns very, very clean. It also burns very hot. Anybody that's ever seen methanol burn will notice that it burns with a blue flame. The only flame that would be hotter than this is a white flame. So, because this is such a clean flame, I'm going to be able to add all kinds of different elements to this, and because they all have different electronic structures, exactly the electronic structure that we talked about, all that crazy 1s2, 2s2, all those energy levels and shells, it turns out for some reasons I'll explain eventually that they all have different colors in the visible part of the spectrum. So, first thing that I learned in a very painful fashion in a middle school once is that make sure that before you refuel your methanol that the methanol is completely out, because what happens otherwise, you turn into Fire Luigi. That actually happened once, and I gotta tell you, it was spectacular. Kids thought it was great, but the whole smell of burning flesh wasn't so hot for me. It didn't feel too good either. So, one of the things that we're gonna do here is we are gonna add methanol to each one of these containers, and we're gonna add a different chemical to each one, and maybe we'll do kind of 3 at a time here just for the purposes of the video here. And so what I'd like you to observe are the different colors that are possible. All of these compounds are also in fireworks that give fireworks their color.
I'm not understanding any of this. Those are white flames.
So this one is potassium chloride, and you guys can just kind of shout out what color you see. You see that?
Yes.
What color do you think that one is? What's the flame test for potassium? Oops, there's a little bit of wind here, so it's going in all of them. What does that kind of look like?
It's like a white and blue, basically.
Yeah, it's actually like a purplish white. It's really, really pale and kind of hard to see. And let's see, this one is strontium chloride. So that's one way that you can get a really nice red color. And that little vortex that you saw there was kind of like the beginning of a little bit of tornado. There's actually another demo where you make a fire tornado, which I should probably go to lab for. This is boric acid. This is what was in the...
Green.
Yeah, this is a green. This is the one that was in the whoosh bottle. Gave it a nice colored flame. And the really fun thing to do is sometimes you can actually get 2 independent flames together.
The red one was out.
Get a little green and a little red. Well, let's get some more red in there then.
After this chair, I'm trying to get some
You can tell my son is super excited about this demo. Conrad, are you not even noticing the fire that's happening in front of you? He's eating cherries. He'd much rather eat cherries, apparently. Everybody's a hater. Okay. So those are a couple of different colors we can get. I just kind of wanted to show you a couple of other elements here.
blue.
So we'll do the same thing. Notice that I extinguished the methanol. I also got the methanol off my fingers. Luckily I wiped it on my pants. Alright, so this one is copper. That's also a green color.
Ooh.
This one I think is probably my favorite. This is lithium chloride. That's what I consider a ghostly red color. Most fireworks have strontium for red, but I'm gonna have a lithium-based firework because I think that better red color. And this one is barium sulfate. That one's kind of a yellowish green. There is another one that I left in lab that's cobalt chloride, and that's one that kind of gives that sparkle to the fireworks. But hope you enjoyed it, and now we'll kind of take a look at why this is happening in terms of electronic structure.
Yay! Clap! Clap, clap, yay! Oh, God. Jeez.
Hopefully this mini video will give you kind of an idea of what's going on in the wizard demo that you just saw. You saw that different elements produce different kinds of colors when I threw them in the flame. And so I just wanted to show you a real quick kind of explanation of what that kind of has to do with electronic structure, just because it's kind of interesting and it might help to kind of reinforce some of the importance of electronic structure. So here we just have a hydrogen atom. We know that a hydrogen atom only has one electron, so the ground state, in other words, the lowest energy state of this hydrogen kind of looks like this, where this electron is kind of buzzing around in a pretty low energy state on this principal shell. So ground state electron configuration is 1s1. What you do when you absorb energy, in other words, like when I threw this thing into the methanol fire, you absorb energy, right? And what happens is that electron kind of gets excited, and it can get excited by absorbing that energy by getting promoted to what's called excited states. And these excited states essentially is like you kicking that electron up to one of the higher shells. It turns out all these different shells exist in atoms. It's just we don't normally talk about them because we almost always talk about the ground state. So that's the absorption of energy. And so what happens when that little electron starts to fall back down, it turns out that only really particular energies of light can actually be emitted. So obviously I didn't use hydrogen in the demo. I could have, but it wouldn't have looked like anything too interesting. But all of these different metals that I threw in there have like a really particular band gap there that releases a really particular photon of light. Those photons of light are, depending on their frequency, all different colors, right? And so if you have some sort of large gap, that's going to produce a different type of light than a small gap. Another thing that can happen is that if we excited, let's say, an electron to a certain energy state or a higher energy state, as it falls back down, depending on where it kind of started from and ends, you can actually get kind of this like mixture of colors, because you might get, let's say, a red with a yellow, right, which would produce kind of an orange flame, or a red with a blue, which would produce kind of a purple flame. So there are all kinds of different parts of the visible spectrum that we can kind of see. This very next slide shows you kind of what you would see if you had what's called a spectroscope. When you looked at particularly hydrogen, you'll notice that if you had kind of something that could see all of the light that is being emitted as kind of a, being passed through a prism, it turns out that if we were to excite something like hydrogen, you'd get something like this with 4 lines, and you can see how that kind of corresponds to these different drops of different energy here. And actually one kind of interesting thing, as this kind of relates to, I don't know, your everyday life, it turns out that there are all kinds of different emissions happening around us all the time. Turns out that even hydrogen gas, when you excite it, there's actually a whole bunch of different parts of this ultraviolet spectrum. One kind of thing that kind of relates to your everyday life is if you look around and look at flowers and stuff like that, you might see some white flower that's just kind of super boring to look at. But if you're a bee who can see a little bit into the kind of the ultraviolet part of the spectrum, it actually turns out that flower would be much more beautiful. So if you ever get a chance, it might be worth kind of looking at what some like boring flowers look like on the internet to a bee. Also, we've got different infrared types of things that can be emitted from atoms. It turns out humans are actually very poor at seeing the potential colors out there. We only see a really, really narrow band. And you can kind of see that in this representation here. This shows you all the different possible regions of electromagnetic radiation. Turns out this little tiny cute little slice right here is all that we can see. It turns out that if we didn't have these electron sublevels, what we would see instead is just the emission of white light. Those of you interested in astronomy and stuff like that, I just included this slide because it turns out this is one of the major ways that we can tell what stars are made of, right? And so if you're emitting light at particular frequencies, there's almost like this fingerprint, right? So if you saw, let's say, some star that's out there, you can look at it with a special telescope and see what the spectra looks like. And based on that, some fancy computer programs can say things like, "Oh, this is a gas giant that contains a lot of sodium and a little bit of cesium and a little bit of neon." Those of you that spend any time staring at those, at like the red light district, which I hope is not true, you see like things like neon lamps and such. And if we were in class, I'd even show you kind of an example that of like an open sign that glows two different colors depending on what gases you put in there. So like if you kind of mixed all these together, you would see like the glow of a neon lamp.